everybody, so today I'm going to walk you through the titration calculations extra practice. So remember, the whole point of doing a titration is so you can figure out the concentration of some unknown solution, acid or base. You can titrate acid to base or base to acid, so let's look at what this scenario is asking us to do. So it says you find a bottle of lithium hydroxide in the stockroom, but it's unlabeled. So to determine the concentration, you have to titrate it. So first think about what type of substance is lithium hydroxide, acid or base. Hopefully you realize with that OH in there, this thing is definitely going to be a base. So this means we are going to titrate a base. The solutions that we have available to titrate are 0.1 molar sodium hydroxide and 0.1 molar carbonic acid. So lithium hydroxide is going to be our analyte here, the one that goes inside of our reaction flask, because we don't know the concentration of it. So if we want to choose our titrant, we have to pick something that's going to neutralize that base. So would we want to use sodium hydroxide or carbonic acid? Hopefully you chose carbonic acid. We for sure want to use that because if we have a base as our analyte, we need an acid to be our titrant. So we're going to want to use carbonic acid here. So if we want to write a balanced chemical reaction equation for the analyte and the titrant, we know that our titrant is going to be H2CO3, carbonic acid. Our analyte is the lithium hydroxide. So take a second to pause the video. What balanced chemical reaction equation is going to happen here for this strong acid, strong base combination? All right, so hopefully you figured out strong acid, strong base are always going to produce water and a salt. So in this case, we're going to make water, H2O, liquid, plus a salt. So our salt here is going to come from the carbonate ion in the acid and the lithium metal in the lithium hydroxide in the base. So if these two things add together, we're making a salt, an ionic compound, which means we need to crisscross charges. So lithium has a +1 charge when it ionizes. Carbonate has a 2- charge when it ionizes. So if we crisscross these things right here, 2 is going to come down and be the subscript for lithium. 1's going to come down and be the subscript for carbonate, so we don't need to write an extra subscript in there. So this means the formula for our salt is Li2CO3, lithium carbonate. And that's going to remain dissolved in solution. So if we take a look at this thing, the next thing we have to do is figure out, is it balanced or not? Immediately you should see, if I have 2 lithiums on the right-hand side, I only have 1 on the left, which means that I have to add a 2 here to help balance it out. Let's take a look at our hydrogens next to see if those balance. So I have 2 hydrogens from the carbonic acid, and I have 2 hydrogens from the lithium hydroxide for a total of 4 on the left. On the right-hand side, I only have 2 in the water, which means I have to double this thing. Next, to check if your oxygens balance out, you have 2 oxygens from the lithium hydroxide, 2 oxygens from the water right there, looking good. So this is our balanced chemical reaction equation. Okay, so now it's time to start preparing our titration. We're going to pour 15.03 milliliters of our analyte into the reaction flask and add 3 drops of phenolphthalein as the indicator. So what color should our solution initially be? Think about what our analyte is, the stuff that's inside of our reaction flask. We said our analyte was lithium hydroxide. So lithium hydroxide is a base. If you add phenolphthalein to a base, what color should you see? Pink. Phenolphthalein appears pink in basic solutions. Okay, the other thing I want you to think about before we move on, why did I give you this measurement to 2 decimal places? If we're trying to be as accurate as possible in our titration, what tool are we using to add our analyte and our titrant? A burette. What's the accuracy of your burette? It's to the 2nd decimal place, to the 100th decimal place. So that's why I'm giving you to the 0.03 milliliters here. Okay, so our analyte is starting out in our reaction flask as a bright hot pink because it's a base. How will we know when our titration has ended, and what does this tell us about pH of the solution? So we know our titration has ended when there's a color change that goes on here. So if we're starting as hot pink, we're adding acid to our solution, what color should we expect to see at the end? we should expect it to turn colorless. And what does that tell us about the pH of the solution? Well, the whole point of a titration is trying to get your moles of your acid to be equal to your moles of your base. So when that happens, we should be at a neutral pH, which is a value of 7. So let's think about this next question. Would you suggest another indicator for this titration? Why or why not? So think about back to when we did our titration in our lab. We were titrating an acid as our analyte and adding a base to it. We knew that our titration ended when we saw a very faint pink color in our reaction flask. If you over-titrated, it meant you added too much base, and you indicated this by saying a bright, hot pink color instead of a very faint pink. If we're going the opposite direction now, we're trying to go from a color change of hot pink to clear. But if you keep adding more acid as your titrant, you can't get something to be more clear, which means it's super hard for you to determine if you've over-titrated your analyte. So if you wanted to get around this, you might want to suggest a different indicator that would tell you something more about the pH. Perhaps universal indicator, right? If you're starting out as basic, you're in that purpley range or purple and blue range. As you head to more neutral, you start turning to green, and then when you start getting into the acidic range, you're going into your oranges and your reds. So if you maybe used universal indicator, going backwards wouldn't be as big of a problem because you can indicate different pHs by different color changes. Okay, so now let's think about the actual titration part of this. You got your base inside of your reaction flask, your lithium hydroxide. You've got your burette. And inside your burette is your analytes, which we decided was carbonic acid. So we're going to start adding in our carbonic to our acid to our lithium hydroxide. And it tells us that our titration requires 3.44 milliliters of titrant to reach the equivalence point. So we want to calculate the concentration of our base based on our titration equations. So let's think about what we know about our titrant. We know that it took 3.44 milliliters of the titrant to reach the equivalence point, and we also know something about the molarity, the concentration of our titrant. So recall the equation for molarity. Molarity is equal to moles divided by liters. And if I know molarity and I know the liters that I added in, I can determine the moles of my titrant. So let's rearrange this equation, and we end up with moles of H2CO3 are equal to the molarity times the volume. So the molarity of our titrant is right up here. 0.01 molar, or 0.1 molar, sorry, 0.1 molar. How much did we add in? Well, we added in 3.44 milliliters, so let's convert that to liters. 0.00344. Yeah, that looks good. All right, so when we plug this in our calculator, 0.00344 times 0.1 is going to get us to 3.44 times 10 to the negative 4th moles of carbonic acid, H2CO3. So at the equivalence point, what do we know to be true? So at equivalence point, we know that our moles of carbonic acid added are going to be equal to our moles of the base. But we have to consult the balanced chemical reaction equation for this again. If we look back up here, for every 1 mole of acid we add in, we're reacting with 2 moles of base. So because this isn't a 1-to-1 ratio, we have to do one extra stoichiometric step. So I know that I have 0.344 times 10 to the negative 4th moles of my acid. So how many moles of base am I reacting with? Well, it reacts in a 2 to 1 mole ratio. So if I take that number and I multiply it by 2, that gets me my moles of lithium hydroxide in solution. 6.88 times 10 to the negative 4th moles. So if I want to calculate concentration now, what do I need to know? I need to know moles, and I need to know my liters of solution. Well, I know moles because I just figured that out, and I know how much of my base I originally started with, 15.03 milliliters. So let's plug this into our molarity formula. Molarity of our solution is equal to 6.88 times 10 to the negative 4th moles divided by 15.03 milliliters in liters is 0.01503 liters. So when we plug this into our calculator, 503, we end up with a concentration of 0.046 moles per liter. So this is the concentration of our base. So if we look back down at number 7, now this is saying if we know concentration, we can learn stuff about our pOH and our pH of our original sample. So we're going to start out with pOH. We know here that lithium hydroxide is our analyte. Lithium hydroxide is a strong base, which means it completely dissociates in water to form Li plus OH minus. So in our original solution here, we have a bunch of hydroxide ions floating around. So this means the concentration that we determined in number 6 is dealing with the concentration of OH minuses. So if the concentration of our lithium hydroxide is 0.046, because this completely dissociates, we can say that the concentration of hydroxide is about 0.046, essentially the same. So if we want to determine pOH, we know that the pOH is equal to the negative logarithm of the concentration of our hydroxide ions. That's its definition. So if I plug this into my formula, pOH is equal to the negative logarithm of my concentration, 0.046 moles per liter. Plugging this into our calculator gives us a pOH of 1.34. So there's the pOH of our original sample. From pOH, we can determine pH of the original sample. Recall that pH plus pOH is equal to 14. So if I want to solve for pH, all I have to do is take 14 and subtract out my pOH value. So 14 minus 1.34. And this gives us a pH of 12.66. This makes sense because our original solution, lithium hydroxide, is a base, so we expect it to have a higher pH value. So here the pH is 12.66, indicating this is indeed a basic solution.